Welcome to this episode on data visualization, part of a series of short films supporting courses I teach in data science and artificial intelligence. You can find more by following me on LinkedIn or as @Binocularity on Twitter. Thank you for watching. Welcome to an episode on information theory and its relationships to visualization. Information theory is about communicating messages, as is visualization, so there is some at least theoretical link between the two, and we'll talk about this in this episode. So information theory came about in the 1940s when a number of people, including Claude Shannon, were thinking about communication of messages and how efficient it could be. And in a number of places this idea of entropy and information came up, and the classic, now definitive paper on this is The Mathematical Theory of Communication by Shannon. He wrote in his paper an important thing that for visualization people we need to understand, that while messages have a meaning, it's not usually the meaning that's being transmitted, it's the message. And semantic aspects of communications are irrelevant to the engineering problem of making sure a message gets from A to B and is reproduced exactly at B. This is an information theoretic pipeline. It models a source sending a message, M, through an encoder, through a channel, through a decoder, and arriving as a message here, M dashed at the destination. That message at the destination, we will assume here, is intended to replicate the message being sent from the source. There are a couple of other aspects to this. One is that the message is chosen from some agreed symbols, an alphabet, like the alphabet of English letters, and is encoded as a signal before it's sent and decoded after it's received, so that the original message need not be the thing that's sent along the channel exactly. Some coded version of the message might be sent. In classic information theory, it also talks about noise and the effect of noise on channels. We won't say very much about that in visualization here. So Shannon abstracts the content of a signal entirely away from the semantics of the message. And when you look at that, one of the things that you can then calculate about signals is entropy. And entropy helps to answer the question of how many bits are needed on average to code one symbol from the message in the signal S. Because different characters in the English alphabet are used at different frequencies, you can use smaller codes for more frequently used letters or frequently used symbols in the message, and that can reduce the communication bandwidth needed on the channel on average. Entropy is usually represented as H, and it measures the information content. You can look at it as or how incompressible a message is, or the best possible bits per pixel you could achieve for a message in a lossless coding system. And you can see here the equation. It's worth sitting down and working through it, but it's essentially calculated from all the probabilities of each symbol in the alphabet being in the message, and it measures uncertainty and information content, very similar things. Smooth messages have very little information content and so can be coded very efficiently, usually, whereas incoherent signals tend to have a high entropy and have little room for compression. So we'll look at some examples to try and clarify what this means. Here's a simple image. This code comes with John Stone's book on information theory, so you can download the images and the code and try it out for yourself. So if all you were ever going to send were images of black pixels, you would in fact never need to send anything, because the receiver, once you'd agreed on your alphabet, which is black pixels, would know you would never be sending them anything other than black pixels. In that case, you can code your message in 0 bits per pixel. All you would need to do to send it is to say, I'm sending you an empty message now, which could be a single bit if possible in the coding system. To calculate this entropy value, you need to know the probability. And since the probability of black is 1, everything else has 0 probability, if you put that into the equation on the previous page, you'll find entropy H is 0. Okay, so let's look at a slightly different example, a checkerboard image. So half of these pixels are white, half are black. you get a probability distribution in the grey levels of all black or all white, so that binary distribution. And now we can say, if you plug this into the entropy equation again, that entropy is 1 bit per pixel. Even if the input is 8-bit grayscale per pixel, we're only using 2, 0, and 1, so that's all we need to send. And this would give you a kind of coding saving of over 87.5% compared to sending the whole image of every pixel and its color value as a 255 or 0 value in 8 bits per pixel. So finally, if we look at a natural image, then in natural images, different pixels are different pixel shades are used at different rates, and so you get a probability distribution depending on which pixels are used. And here, if we just calculate the entropy for this image, we can find an entropy of 7.84. If we only ever sent pictures a lot like this, and our alphabet worked for them, then we would get away with 7.845 bits per pixel instead of 8 bits per pixel, which let us save about 2%. This is therefore relatively a high entropy or high information content image. In real life, of course, when you're coding images like this, JPEG and MPEG coding is lossy, not lossless, and so it is throwing information away that it thinks you won't see. And at some point, of course, you do see it. You see the artifacts in those things, but it hides very well the information loss. And here we're talking about lossless coding. It's quite different from the practical lossy coding systems that MPEG and JPEG use. An important class of signal is to consider what happens when you have white noise. So white noise would be an equal probability of any value in the grayscale appearing in the image. And here again, 8 bits per pixel. If we calculate the entropy for this particular grayscale image of white noise, we get an H value of about 7.991 bits per pixel, which is a tiny saving over 8 bits per pixel. And to give you a more intuitive feel for that, perhaps, it's going to seem odd that a noisy picture like this has any information in it at all. It's just like static on a TV screen. But imagine this was a view of a star field, and each pixel was representing if there was a star present or not and its brightness. So you get location and brightness of stars. There will be a lot of stars in this picture, up to 65,536. And in that sense, it's conveying a lot of information. So here, entropy would correctly capture the fact that there's a lot of information in here, and it's hard to compress that information because it's small and there's little coherence in there. If you want to use lossless entropy coding to code images in general, then you collect a training set of many images and work out the probabilities of which pixels are being used. And that would give you a way to create an alphabet for these things. There are better coding methods using difference coding, particularly in video where you difference frame to frame and you just send the difference rather than the whole image, and that lets you code losslessly more efficiently. But at the end of the day, you're also showing humans the images, and remember, we've got limited perceptual abilities, and you can exploit that, and JPEG and MPEG do this extremely well. They'll, through experiments, so I was on the MPEG coding committees for several meetings a number of years ago now, and they run very rigorous trials to see what it is that they can leave out of images and people won't notice. And the best algorithms, the best approaches win and end up in the standard. A summary of entropy. Entropy is a concept that pretty much underlies all data science. What's the information content in a data set? It gives us a measure of information or uncertainty in a signal without concern for semantics, which is the more difficult part for us as visualization people. On average, if it will tell you the number of bits you need to losslessly code a symbol for in a single transmission, given a pre-agreed alphabet of symbols and their probabilities of appearing in the message. And you can also consider it as a metric for comparing signals. So in ECG trace comparisons, approximate entropy and sample entropy are used to detect when heartbeats differ. So if your heartbeat is becoming more entropic, having more information in it, it tends to be an indication that there's something wrong with your heart. So measuring the entropy of a signal can also be a diagnostic tool in some cases. But practically a signal in this sense is anything, any piece of information that you need to code and send and decode. And there's a number of key theorems around this. the source coding theorem, which says what we've been talking about, you can't losslessly code better than H, and the noisy channel coding theorem, which defines how much you need to put into signals, how much redundancy signals need for a given error rate. But we're not really going to talk about that in more detail just yet. There's a great video here, and I firmly recommend John Stone's book. So if we go back to our picture of visualization, how does that look from an information theoretic viewpoint? You can divide the pipeline of sending a visualization into these different stages, which is more straightforward than it looks. So on the left, you have a digital system taking data, mapping it to geometry and colors, and rendering it, producing an image which is put onto a display. In the middle, that display turns the image into light waves, which are transmitted through space, through the visual optics and into your eye. And then the decoding part of this, the human being part, is the bit that sees that, detects it, perceives it, and starts to understand it. It goes through the visual cognition system and it ends up in memories and wisdom and culture. And there are two key functions here. One is the signal coding system on the left, and the one is the decoding system on the right. And the coding system is digital and uses computers and is under our control. And the decoding system is not. It's a human being with a brain, and we don't fully understand how those work yet. So digital information moves to optical information, moves to neural information. And along the way, many forms of noise can be added. We can get information wrong in the digital side. We can have it interfered with optically. And at the end of the day, the brain adds its own information. It adds ideas and theories about it, which might change your memories of what the information was. So in Shannon's terms, the destination was a mechanical decoder. In visualization terms, humans are far from ideal receivers of messages. We're not mechanical decoders. We change them, we add to them, and we in visualization need to understand in some ways what the limits of our visual systems are and our cognition systems, so we can design visualizations which fit the capabilities of the visual system and the mind to take information from a visual signal. Within this framework, visualization lends itself to an empirical psychometric approach to determining what works. So we can try things out in images, we can test if people have received the messages, and we can look at how many people will receive the same message given the same picture. And that's really what we're after. We're not art designers, we're not looking to produce conflicting and different responses in people. We're not looking to challenge people's thinking in an artistic way, but we are looking to convey the same information to everybody if we can, so that there will be some agreement if you ask people on what a visualization meant. So on the left here, information theory talks about bits and coding bits, and on the right, visualization theory talks about ideas and meaning and understanding. And we can see this in the data to wisdom pyramid. We have data going to information, going to knowledge, going to wisdom. The lower layers of this are really very information theoretic. They're digital information. And then the upper layers move into human psychology and psychophysics. How do people think? How do people understand things? How do people make decisions based on information that they're receiving? So some of this is computer science and engineering, and the further up the pyramid you go, it gets more and more into psychology and cognitive visual science. So some great references here. You'll find those in the slides.